right? Finished up chapter 1. I feel like we said that we were going to review something right before we, right after we finish up.
Well,
We finished the last balancing equation. Okay, so here are the chapter 2 slides. So take one of those, pass them around, and here we go. So we started off, or this chapter starts off talking about, reminding us the difference between a physical property and a chemical property. All right? Physical properties of material, matter, right? Things like its color, how big the piece of material we have maybe, the melting point, the boiling point. Why isn't the melting point of a substance a chemical property? Do you guys remember that? Why isn't the melting point of a substance considered a chemical property? What happens when we melt something? What if we say happens? Can we talk about this? H2O solid goes to H2O liquid. What's the difference? What's going on here? What are we doing to a substance when we heat it? What's that? Okay, we're making it move faster, right? We don't really get into it in details until chapter 5 or 6, but the energy that we put into a system becomes its temperature, right? Temperature is just our way of measuring how fast the collective molecules or units of the matter are moving. Okay? So you can think of water molecules, right, interacting with their neighbors in such a way that, so these dashed lines are interaction with their neighbors, right? In such a way that, something like that, that there's some stickiness, these dashed lines, right? The water molecule itself looks something like that, but we can change the color maybe. The stickiness between molecules and the ability of those molecules to stick together depends, or is the depending factor to determine whether it's going to be a solid, liquid, or gas at the given temperature. All right? So if you heat something, you overcome these barriers. In the case of solid, then the water molecules will interact, but not as tightly, and so those interactions become less pronounced, right? And the result is you get a liquid. If you heat it up even more, and it becomes gas, then the water molecules now are completely independent of each other, and there's no interaction that's causing them to stick together. So we're changing the matter, but we're not changing, in any of these scenarios, how the hydrogens and oxygens are interacting with each other. We're changing how the water molecules themselves are interacting with each other, right? So, boiling, melting, right, freezing, all of these things are physical changes, they're not chemical changes. A chemical change generally has to do with how the chemical responds with a different chemical, right? So you take two chemicals, they react and form a new chemical, and then we have different words like reactivity or oxidation or corrosion, right? These are different words that have to do with the chemical changes that will occur between two different chemicals. Now, this is also a review. We know about solid, liquid, and gas. And aqueous, do you feel like you understand what aqueous means okay? Anybody want to tell us what's aqueous mean? It's dissolved in water. What is a suspension? What's the difference between a solution that's aqueous and something that's a suspension? Can a suspension be in water? Yeah? Milk was our favorite around in the solution. However, when something is actually dissolved in water, like when you put salt in water, it's transparent. You can't see any of the salt. If you put lemonade in water, it's colored, but it's still there. Yeah.
What was the definition again of suspension?
A suspension, it's a solution. Well, not really a solution. It's where you have a solid dissolved in solvent, but the solids aren't actually dissolved, they're just suspended temporarily. So, the chunks, the particles themselves, are still aggregates of molecules that are trying to be dissolved. They're still microscopic as opposed to molecular, where the molecules will actually separate completely. So let's look at this for an example. Here's sodium chloride. I drew this once, right? You guys remember this? You should try it at home sometime, right? It's fun. Remember this? What am I drawing here? What is this thing? It's salt, right? Sodium chloride. And it doesn't just go in 2 dimensions. It goes in what? 3 dimensions. All right? Now, when we put something like this in water, it will dissolve. And that means that the water molecules come in here and surround the ions, the different units. Sodium and chlorine here is what we're dealing with. So the chlorine gets surrounded by these water molecules. Not just 1, not just 10, but hundreds of them gather around to have a party with these individual units, right? And so that one will go away, and then this one's now available. So this one gets sodium at a positive charge, so it directs the oxygen on these water molecules. I'm not going to draw the hydrogens on there, all right? So individually, each one atomically is removed and separated. In milk, you have relatively large chemicals called triglycerides, fatty acids, right? And these will form clusters of things like micelle, or like kind of like bubbles. I don't know if you guys have taken some biology where they talked about the double layer of a cell, right? Phospholipid bilayers. I don't know if you guys are familiar with that. But in milk, the actual particles or clusters that are being surrounded by water molecules and homogenized into solution are much larger, And that's why you can't see through it. Light won't, I mean, you can, it's a little bit of translucency there, but you can't see through it. So suspension is where the actual units are microscopic as opposed to atomic or molecular, depending on what you're dissolving in. A balloon? Yeah.
Versus like the dust that's in the air. What would the balloon in the air that would be suspension?
Okay.
The dust, would that be the one?
Sure. Sounds good. Sounds good. In terms of maybe thinking about size, because this thing would be super duper tiny, right? And this thing would be very large, right? Okay. Good. So then, physical change and chemical change. You find yourself a neighbor and see if you can find out which one here is the physical change, right? Or after the physical change. Did everybody see the roll going around? Okay. Make sure it makes its way over here. Did everybody get it? Anybody else get the roll? Okay, great. Why don't you just hand that forward then? Did you find it? What do you guys think? Which one is it? D? Okay, good. So, should we go over them? Anybody want to talk about any of them, or pretty clear? All right. Great. I think I told you, but I will probably tell you multiple times throughout the semester. It is your responsibility to raise your hand if you don't know something when I say, hey, do you have any questions like this? Or who got that one right? Or something like that. It's your responsibility to let me know. I mean, it's embarrassing maybe, but that's what learning is. If you look it up in the dictionary, learning equals embarrassment, right? You need to put yourself out there and realize the things you don't know. So, question?
And second thought, so for C, when the sugar turns dark brown when it's heated, what makes that different from as like when you heat water and evaporate?
Okay, good. I mean, you know, there's no reason that we know exactly what's going on at the chemical level when sugar turns black. So if you didn't know this, there's no reason to be surprised. But when you get sugar, what was our chemical formula? Did we kind of identify what we're going to use for sugar? C6H12O6, and I know that this isn't sucrose, which is what they're probably referring to, but it's very similar in structure. Okay, it's a carbohydrate, and all carbohydrates have this general formula, basically. So when you combine it with oxygen on a stove and heat it up really strong, then you'll get carbon dioxide, but you'll also get just carbon and water. All right, so those are some significant changes. And sometimes it gets pretty stuck on the pan, right? Pretty solid, hard stuff. That's the carbon that's just hanging out there. It'll usually dissolve, right? Because sugars are easy to dissolve generally. Even if it's really hard, it might take some time. Okay, any others that we want to talk about? All right. Moving forward. I'm going to try to get past some of these. Okay, units. It's important that when we talk about anything in life, we ensure that we're using the appropriate units, right? Like if I say, I went to a movie last weekend, it was really good. All right, you just heard it. Did you hear it? How good was it? Really good. If I say, I went to a movie last night, it was really good. Which one was better? The first movie or the second? How much better was it? So, some things we don't have ways to quantify very effectively, right? We'll say, how many times have you said, I'm going to watch a movie tonight, let's look something up on Netflix or whatever it is you look it up on, and it has 4 stars. Like, oh, it must be a good movie. Right? So often, it's like, what? How in the world can anybody think that that was worth an hour of your time, let alone 2 hours? So, I mean, we have something that we just can't quantify. I remember being on my mission and telling people, we have a message that will make you happy. I don't know if you guys ever tried that. What do they usually say? I am happy. Oh, well, this makes me more happy. Oh, I'm happy. Oh, but you can be happier. No, I'm already happy. Too bad there's not. But this could make you 7 happy. Oh, okay, well, tell me the message then. So, quantifying things and using the correct units is not just a good idea. It also allows us to visualize how to answer problems that we don't understand. And that's extremely valuable because there are going to be questions as we proceed, not in this chapter, but upcoming chapters, that you have no idea how to answer, but you can tell based on the units that they're asking for, how you have to arrange the problem and get the answer. All right? And to me, that's real learning, because you've essentially been given something that you know nothing about, but your ability to learn how to learn kind of allows you to answer those questions. Okay, so the units are important to become masters of, right? So let's talk about, here's another example. In 1999, there was this Mars probe that was going to go around Mars and take beautiful pictures. But there were two teams of engineers, one from different parts of the world, where they used different units. And they knew they used different units, but they never had a conversation about whose units they were going to use. And so both of them were polite and used the other one's units. And so it ended up that they weren't giving as much fuel to the system as they thought they were, and the thing wasn't behaving like they thought it should, and it crashed into Mars, right? So they lost their spaceship because of units. And then even a sadder story, there was a conversation between two people. One said, I saw the biggest hot dog in the world the other day. And I said, yeah, I've seen that one too. No, this one was big. It was 60.3. And the other one said, yeah, I saw that one. Right? But instead of saying 60.3, you should have said 60.3 what? Something. Meters, right? This was the biggest hot dog in the world when I took this picture, but I didn't take the picture when I looked into it. Anyways, some common units. Becoming familiar with common units is helpful, but in reality, you're going to go into a lab, a line of research, where they have their favorite units, and you're just going to have to become familiar with it. It's nice to know that there are standard units, but wasting our time to kind of memorize all of them, I have not found it to be terribly successful. So being aware of them is what we want more than anything. Okay? Temperature is an interesting one, because Celsius, Fahrenheit, Kelvin, why we have all three is kind of an interesting story. It started off, Celsius and Fahrenheit were two glass blowers who could make really long, thin glass, so they started making thermometers. But at that point, we didn't understand that temperature was related to kind of the motion. Oh, I just erased our beautiful water molecules, right? But we talked about when you got colder, the water molecules were moving less, and so they would stick together more, right? And that's the case. If you think of water molecules, or any molecules, their movement being related to kind of the temperature of them, put your hands up here and pretend like they're little water molecules. And show me hot water molecules. Good. Show me cold water molecules. Very good. And then really cold water molecules. Let's see who can get the coldest water molecules. The coldest, the coldest, the coldest. You know what I'm saying? Oh, there you go. The coldest, the coldest, the coldest. See, there comes a point where what? You can't go any slower, right? So negative 200 degrees Celsius, or 300 degrees Celsius, sorry, doesn't exist. There's no such thing. You just can't get any slower than still. And when they realized that, they started a new system, Kelvin. They hijacked Celsius's graduates, so the space between Kelvins are the same as Celsius's. But Kelvin starts at 0, meaning no motion, and then works its way up in units of Celsius as fast as you want, right? See, I go really fast. See? Really good. I get a lot of exercise because I can teach all the time. All right, so you can derive units that you might not be able to inherently think of. And that's kind of what we were alluding to. That is 1 meter. And now I want to find the area of this square, and this is 1 meter. The area, 1 meter times 1 meter equals 1. The units have to go along, right? We don't do the math without the units. Okay. So another important component are the prefixes. The prefixes for the values that you're trying to express. And this was a conversation I had at one point with somebody. Except for we didn't say 0.000000001, right? We used the prefix to make it sound more reasonable, right? So it really doesn't, it's not useful if you don't start to use the prefixes. You can't, the numbers get too large, too small, you can't talk without understanding the prefixes. So we have to make sure that we begin to use the prefixes. We don't want to have to labor ourselves with every single one of those. Let's choose the ones that we're going to use most frequently. And I think most of those you already know, but maybe you don't know it. We'll have a little conversation here and see what we already know. Anybody deal with this sort of thing when they were a kid? Right? The ones that are kind of like the size of your thumb or whatever, the thickness of your thumb, or maybe your pinky or something, are what? What do we call those ones? No ideas. Okay. So this one has 100 of them. Does that help? Centimeters. Centimeters. Good. So we have centimeters. And that's one I want you to be familiar with. Now I think that we know them, even though you're pretending like you don't. And I think we also have a hunch what centa refers to. Meaning what? 100. What words do we have to remind us of that? Century. Centipede. Percent, which means per divided by 100. What about cent? What does that refer to? 1 penny, right? If you're talking about a dollar. All right, so centimeter is 100. And these centimeters are broken up into little lines. You guys remember that from grade school, right? What are those little lines called? Millimeters. How many are there in one of these centimeters? There's 10. There's 10. All right, so that's going to get us where we need to get with millimeters. If there's 100 centimeters, per meter, how many millimeters are there per meter? 1,000, because it's 10 times 100, right? All right, good. Now, let's do this in scientific notation, right? 1 times 10 to the what? Per centimeter. Just 2, however many zeros there are, right? And then this one is 1 times 10 to the 3. So, centa and milli, I think we know, but if it takes a little review, let's get to know it. What's after milli? I don't think we know this one very well. Micrometer. And micrometer is not 1,000, but 1,000,000 in 1 meter. 1 times 10 to the 6. And then nano, we used to have this thing called the iPod Nano. Anybody have one of those or ever heard of them? Okay. I was so excited when this came out, the iPod Nano, because I thought, oh good. Because I used to work on nanochemistry, making nanoparticles and interacting with enzymes and making nanoparticles and complexes. And I thought, oh, great. They're actually using nanotechnology to make something, because they call it the iPod Nano. And that was about the time that everybody was excited about nanotechnology. And it was really a cheap, well, amongst the scientists, when we realized that there was nothing nano about it, I was really put off. But, you know, they tricked me. I didn't buy one, but because of that, I was going to. But nano kind of is easy to remember because nano sounds like 9. And there's 9 zeros. 1 meter, 1 times 10 to the 9. So those are the ones that we need to learn how to become familiar with and use whenever. All right? Going the other way, not just fractions of a meter, but multiples of a meter. I think you guys should know this. I'm kind of always surprised that you guys don't know this sort of thing, because whenever my phone says you can't install that because you're out of space, I have to free up bytes, which is memory on my phone, right? Does this happen to you guys ever? All right. And so I thought that people would know what a byte is and what a kilobyte is. KB. What's larger than a kilobyte? Megabyte. And then gigabyte. Right? And we don't need to talk about bytes. We can just use kilo, mega, and giga. You guys know how many bytes are in a kilobyte? Or let's say kilometer. How many kilometers are in 1 meter? 1,000. Well, sorry. Other way around. 1,000 meters in 1 kilometer. Right? There's another name for a kilometer. What do they call it? What's the other name for a kilometer? A kilometer. Right? Have you ever heard that one? All right. So 1 times 10 to the 6th. 1 gigabyte. 1 times 10 to the 9th bytes. Or meters, if we're talking about meters. Gigameter. There they are. There's like 7 things that you really have. A terabyte also, some point it will become the thing. Does anybody know any terabyte hard drives? Yeah? Good. Excellent. So we are familiar with these already. Here's a little chart that we can fill in to show our expertise and to help embed this into our mind a little better. Okay, so take a little time, do this with your partner, make sure they understand what's going on. I told you how to talk to your partners, right? So let's practice that. I'm going to go get a drink. Figure out what we're supposed to be doing here? Yeah, I think that's right. Good. Good. So, 10 to the 9. So you have to do something. Good. Okay, so looks like we're getting it. Concerned about your guys' groupness. You guys okay?